TEDxNTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D. Greetings, everybody. Greetings from Singapore. And today we have a guest, Mr. Syed. Syed, welcome to the HIT podcast.
Oh, thank you. Thank you for inviting me.
All right, you're most welcome. And today's host is myself, Christopher Luanga, and
Ahmed Hussain.
All right. So as we usually do, we would like to just get a little bit about you first, just the person, how did you get here? Tell us who is Syed for our audience.
Right. So I've been a very simple guy. I mean, I did my schooling and education entirely in my hometown of Bangalore, India. So I haven't really been outside of Bangalore, especially for education purposes. So the very first time I've come out for education is Singapore. And life's here slightly different than life back in India, right? So adjusting to it took me a little time. But yeah, I've been fond of science. I've been fond of chemistry. So I took chemistry as my discipline in my senior high school, and then my undergrad, I did chemical engineering, did a lot of internships and research scholarships, and then applied for direct PhD. I avoided the master's route, so applied for direct PhD and got it here at NTU. So this is my final year now. I'm almost headed towards the final semester. I'm 25, so hopefully I get my PhD before I turn 26.
Okay, nice. Makes the rest of us look old getting that. Right. Okay, great. Cool. So Bangalore is more software tech city because from what I know, it's a technology city. I'm wondering what is the focus as a city? What would you say is the focus?
It's known for two things: the startup culture, because a lot of venture capitalists, angel investors, all of them reside in that particular part of town, and also the IT, right? So that you have a lot of tech parks, right. And we attract a lot of talent from all over India. So they migrate to Bangalore, and then they work in a lot of IT firms as in different capacities. So Bangalore's local population has been steadily declining. So it's always been people coming from outside of the state for to migrate for jobs and just better standard of living, I guess. Yeah.
So then, why did you kind of went, into the chemical engineering part? Is that
right.
Still a common thing? Like people choose different.
No, it's not. Many people in Bangalore still prefer to go the software route. Maybe CS, instrumentation, IT. All of these are very hot topics in Bangalore. But that's if you want to work in the same city you've grown up in. I chose chemistry and chemical engineering, and I wanted to move out, maybe seek life abroad. So, experience different cultures. So yeah.
All right. So you are in India, then you want to study abroad. Yeah. Then tell us about what then did you decide to study? Broadly speaking, what field are you in? What are the general problems that your field handles?
So many people have this common misconception that chemistry and chemical engineering are related. They're very different topics. So chemistry is just a tool. Chemical engineering is just the application of things. For example, chemistry is making paint, but upscaling it, right? Making it an industry out of it, having it automated, making sure that every part is working properly. That's chemical engineering. Like scaling everything from the beaker scale to, let's say, a reactor scale, right? That's the engineering side of things. Nice. Chemistry is just making something novel in a lab, but chemical engineering is just like, applying it at higher levels.
That's an interesting distinction. Okay.
Yeah. So after 4 years of studying chemical engineering, I decided I don't want to be one of those people who wants to change disciplines, because there is no point that you study 4 years in a discipline and then you change and do, let's say, any other job, right? A lot of my peers opted to go for an MBA. Some even have chosen to go for become a lawyer after 4 years of engineering. Yeah, but I decided to stay in the core discipline. It's just a principle of mine. which better way to go than to go to the top of the pyramid, right? So the pinnacle of education is probably doctorate philosophy in your field. So I opted for this. Yeah.
Did you have any other opportunities other than PhD? Or did you look for any other?
Yes, I did. So a lot of my friends applied for masters in the US, UK, and I also did apply for masters. I got a few offers, but I still had my heart set out for PhD. And getting a direct PhD in the US is slightly more challenging because of funding opportunities and scholarships and so on. Especially a direct PhD. Yeah, without a master's, you need to be like a really brilliant student.
Right.
Yeah, and have like some attractive funding. Yeah, it didn't work out for me, but NTU is a very welcoming university and gave me an opportunity. Yeah.
All right. So you're now in the field or the work that you do right now. Can you give us a taste of what it is before we focus very much into it? What is it?
Sure. Yeah. So historically, how it's been is that after all the industrial revolutions, we as humans rely a lot for our energy needs on fossil fuels, right? Most of our heat and electricity, especially, comes from the burning of fossil fuels. Coal, oil, and natural gas constitute most of these. So what generally fossil fuel is, it's a carbonaceous source. So you have carbon, you burn carbon, it produces CO2. You burn carbon in the presence of air, which has oxygen. And when you burn it, it's an exothermic reaction. You have hot flue gases coming out, say 1200, 1300 degrees Celsius. Those hot flue gases can be used to run a turbine, a gas turbine, or they can in turn heat up, let's say, water to produce steam, and that steam can be used to run a steam turbine, right? And what happens to those flue gases after they've done moving the turbine? They just release as exhaust, right? So you have these stacked gases and they just release it all into the atmosphere. That's why the atmospheric CO2 concentration today is about 420 ppm. It was
420 parts
per million.
Per million.
That's about 0.04 volume percent, right? And 10 years
Tell
ago,
me, is that a lot or what?
That's quite a lot. Yeah.
Okay.
We've hit the record high for the past 3 million years. For the past 3 million Earth years, we've not had such high concentrations, right? And it's bad in a way because CO2 is a greenhouse gas. What it does is a lot of the sunlight which comes from space, from the sun, right? Earth tends to absorb, right? Sunlight is just a mixture of a lot of radiations. Could have visible, UV, infrared. Earth tries to absorb some heat and also radiates back some heat. So you have the atmosphere, which is like a blanket, and you have incoming rays and then radiation going back. If you have a lot of CO2 build up, it builds like this blanket and it absorbs all the infrared, which is supposed to go back to space, right? In doing so, it just keeps the heat within the earth. And then that heat buildup has caused global warming, climate change, right? You have sea levels rising, you have floods in various areas, you have heat waves in certain parts, and you have displacement. So a lot of issues caused by climate change. What we try to do is tackle this problem through our research. So we focus on fossil fuel generation power plants. So most of Singapore's grid is powered by natural gas, right? 90% of it, more than 90% of it is powered by natural gas. And there are very few carbon capture plants. When I say carbon capture, it's you try to capture all the flue gas coming out and try to redirect it to, let's say, underground reservoirs, or try to use that CO2 instead of just releasing it to the atmosphere so that the concentration does not increase. In my research, we try to replace this old concept of fossil fuel generation and try to implement a new system where the outgoing flue gas can then be directly stored underground. So when you burn, let's say, coal, oil and natural gas with air is about 79% nitrogen and 21% oxygen. So the carbon is burned, it utilizes all the oxygen, but there's still a lot of nitrogen in the flue gas. And separating the two gases, nitrogen and the product CO2 from one another, is a very energy intensive process. That's why carbon capture is costly, because you have to separate the nitrogen from the CO2 and then take away that CO2 from, right? So what we try to do in my research is burn the carbon fuel with pure oxygen. So when you burn it with pure oxygen, the outlet stream is 100% CO2. There's no dilution with anything else. So
let me understand this.
Yeah.
In today's world, we burn we do combustion with the oxygen that we have, the regular one.
Yeah.
And the system you're trying to implement is one that uses pure oxygen.
Pure oxygen, yeah.
Where do we get that, or how do we get that?
Yeah, so it's not pure oxygen. So producing pure oxygen also is a very costly process, right? So you have to do liquefaction of air. You have to liquefy air. It liquefies at negative 180 degrees Celsius. So that's a lot of energy right there. We don't go that way. What we do is we try to utilize these solid oxides, right? For example, iron oxide is Fe2O3. It's just common. It's found in red mud, right? Okay. Sediments of red mud. It's a solid oxide.
All right.
By property of this solid oxide, it's able to donate its oxygen atom. So Fe2O3 can be reduced to Fe3O4, which is one lower oxidation state, and it goes to that lower oxidation state by donating oxygen atoms. Mm-hmm. And this happens at high temperatures and pressures. So if I were to put in, let's say, coal and iron oxide and pressurize the system and have high temperature, that coal will burn using the oxygen from the iron oxide, and that iron oxide will be reduced to Fe3O4. Now, once that is done, I switch the gas to air and regenerate the Fe3O4 back to Fe2O3. And then this cycle keeps on happening, right? So in one state, I can supply natural gas to Fe2. Let's say I have a bed of iron oxide. Mm-hmm. I supply natural gas. All the natural gas gets combusted. All the Fe2O3 is converted to Fe3O4. Mm-hmm. And then once that is done, I try to regenerate it by passing air, right? Fe2O3 absorbs all the oxygen from the air and lets go of all the nitrogen. Hmm. Right.
So you're kind of using the iron as a vessel.
Yeah.
Like oxygen vessel.
Yeah, it's what we call an oxygen carrier. Mm. Yeah, so that's the technical term for it. Yeah.
Wait, so let me still understand it a bit clearly. Yeah. So you have methane.
Yeah.
Right.
Yeah.
Then you put it close to the FeO3.
Fe2O3, yeah.
And then Fe2O3, and then you end up with
CO2. CO2 and water. So the hydrogen from methane also combusts to water.
Right. So you have water and you have CO2.
Yeah.
Then what do you do after that?
So that CO2 and water is passed along. So those are flue gases, right? So those are high temperature flue gases.
Right.
And those will be passed to, let's say, heat up water or run a gas turbine. Yeah.
Okay.
So, and in the meanwhile, you can have another reactor where this spent iron oxide is sent to be regenerated. And you can have this cycle going on where one cycle of spent iron oxide is being sent to a reactor to regenerate, and then the regenerated iron oxide is being sent here to combust.
I'd like to take a step back first.
Yeah.
Can you maybe tell us about other approaches that were already established before?
Yeah, so there have been. This is like a fourth generation. So what we call this is chemical looping combustion, because it's the looping of a chemical through different reactors. Mm-hmm. There have been 3 generations. So you would have heard of this thing called post-combustion capture. So post-combustion capture is where you have your regular combustion going on, right? You have coal being combusted and you have your fossil fuel coming out. You try to wash that gas with, let's say, a solvent, some sort of amines, right? So amines are able to strip off the CO2 and dissolve them. So you dissolve the CO2 in one of these liquids and then you heat up the liquid and the CO2 will escape. So that's one, but it's very expensive and very energy intensive to actually regenerate those amines. So post-combustion. Then you have something called pre-combustion. Pre-combustion is where you try to take away the carbon from the fuel before you actually ignite it. So let's say you have CH4 methane coming in. You try to do steam reforming. Steam reforming is where you pass steam through the fuel and strip away the C part of it, the carbon part of it, right? And capture it separately, and you just have hydrogen. And hydrogen is the cleanest fuel possible because it just combusts to water.
So you remove the carbon even before
so that's pre-combustion. Again, pre-combustion uses a lot of sorbents. You need a lot of energy for sorbent regeneration, and it's not viable. There's very few pre-combustion carbon capture plants in the world right now. And then finally you have what you call an oxy-combustion plant, right? Oxy-combustion is where you combust in pure oxygen. Instead of having air as the oxidant, you supply pure oxygen, 100% oxygen.
Right. Okay.
Yeah, but getting 100% oxygen again is very difficult. You need to have cryogenic separation plants where you separate the constituents of air from as nitrogen and oxygen, which is the 2 major parts. Yeah.
But that's sort of you sort of took one step beyond this.
Beyond this,
approach,
right? It is. So chemical looping kind of comes under the umbrella of oxycombustion because we still have just pure oxygen
Right.
coming in, but the source is different. Yeah. And another metric to evaluate these carbon capture plants is their efficiency. So you guys know that all fossil fuels have some sort of thermal energy, right? You call that the heating value, like the calorific value, right? All sorts of fossil fuels have it. So let's say I have coal, which could say have 30 megajoules per kg. So if I have 1 kg of coal, it would have 30 megajoules of heat. But if I were to heat it, the amount of power I can generate with the turbine could just be about 10, right? 1/3 of it. I could only get 10 megajoules at the end.
Right.
So in the process of conversion, we lose 20 megajoules, right? So the efficiency of power generation is only 1/3, 33%. Yeah. So most of the traditional power generation plants are about 30 to 40% efficient in that they only give you that particular energy at the end. Most of it is lost in heat losses. Yeah.
Yeah.
Honestly, when I learned this, I was very surprised. I the first time I was like, is that what happens? Like 30% is all we get out of
Yes.
whatever we put in.
Same with
It's quite sad.
with cars, right? With
Yeah.
And cars are even worse, right? Because
combustion engine.
generally the engines are, I guess, not made to as high. I assume to make so many in a short period of time, they cannot make them to such high efficiency levels. So it's not great.
Yeah.
Okay, so your method, when you say that it captures the carbon, it's after the burning because you're burning using Fe2O3, right?
Yeah.
You still get water and CO2.
Yeah.
But what you're saying is that there is now no nitrogen.
There's no nitrogen dilution. Yeah.
So because of that, what is the?
It's easy to just capture all the carbon.
Okay.
And CO2 is not a bad gas. It's bad if it's in your atmosphere. But if you've captured it in a pipeline, you could transform it to many chemicals. You can transform it to methanol, which is a good source, right? You can transform it to specialty chemicals. CO2 utilization is just another subject altogether, which many people work on. So if you have CO2 as a starting product, you could have hundreds and hundreds of other products you could make. Yeah.
So give me just a quick chemistry lesson here. Do we need the carbon in the burning, or it's not needed? As in
We do.
Okay,
carbon is the source of.
Okay, so the carbon is needed. That's why we have coal and wood and so on.
Yeah.
Okay.
Yeah.
Because the other time you mentioned that you remove the carbon.
Yeah.
And then like methane is CH4, right?
So once you remove the carbon, you still have hydrogen, right?
Right.
So hydrocarbon is basically just hydrogen and carbon, and both of them are efficient. So burning of carbon and hydrogen are very exothermic reactions. So you have a lot of heat produced. And in fact, coal is ranked based on the amount of carbon it contains, right? So you have something called anthracite, bituminous coal, peat, and just coke, right? And these are different ranking of coals based on the amount of carbon it contains. So let's say 40 to 50% carbon would be anthracite, bituminous would be somewhere around 30 to 35%. Yeah.
Okay. So energy density wise, methane and hydrogen, which one is more dense?
I think it's hydrogen's more dense on a mass basis.
But volume is I guess okay.
And how is the capturing of carbon done? That's that's also a different area of research.
Yes. So carbon capture, it's called CCUS. So there's carbon capture, then utilization, and then storage as well. So if you don't have any use for the carbon, you could just store it underground, right? So when you have carbon capture done, you have CO2 pipelines going in, and you could store it in like deep aquifers, ducts, rock formations, and just leave it there for hundreds of years. It's just carbon underground. It could solidify. After hundreds, so it's just fossil basically. Yeah, but utilization.
Do we always get carbon dioxide, or sometimes?
Yeah, it's just dioxide because it's burnt, right? So combustion is just adding oxygen to something. So C plus O2, just CO2. Yeah.
But there's gotta be some carbon monoxide there as well.
Yeah. Right? So if you have partial oxidation, you could have some carbon monoxide as well. But you have to make sure that the combustion is complete. Yeah.
Okay. So let me try to understand. So the rest of the process is still the same. We burn, we get CO2 and water, and then we send it through a turbine or whatever we are using to extract the thermal energy from that system.
Yes.
But after that, you put it through your system where it's put underground or used to create other chemicals.
Other chemicals, exactly.
Okay. So let's go specifically maybe to the specific things you do, or the, I guess the tools you use to actually do this miraculous work. Can you tell us more about that?
Sure. First, let me take a step back and explain why this is done. Why we're relying on fossil fuels, especially because I know historically it's been this trend, but now there's a lot of talk about renewable energy, right? Why we're not shifting towards renewable energy? Why we're relying heavily on fossil fuels? Because it's estimated that we only have about 50 to 100 years of fossil fuel left, right? So we're going to run out of fossil fuels. Yeah, at some point we're going to run out of it, and we need to have alternative energies. So why is the research not focused on renewable energy? And the main thing has to be done with cost and infrastructure. Renewable energy, for example, let's say solar and wind also. Wind has a lot of geographical limitations. You need to set up wind turbines in places where there's strong wind currents, and you're able to capture all that. Even solar, right? So you need to have you don't have sunshine all the time, but even if you do, you have to store it for, let's say, cloudy and rainy days. So you need a lot of batteries to store that solar power. So renewable constitutes very little of the whole power grid mix, right? I think in the US it's only about 14%. So 14% of US grid is just powered by renewable, but the rest is still fossil fuels right now. So we can't rely on for renewable energy to power the entire system. And it's also got to do with not at the individual level. So people often make you feel guilty that you as the end consumer are responsible for climate change, and it happens at the very individual level. But actually it's got to do with businesses, right? It's the big businesses and the big companies, schools, hospitals. All of these people have to try and switch and try to adapt.
Correct.
So because when these people are the largest emitters, right? The biggest industries emitting CO2 are actually the transport industry, the cement industry, right? The power generation industry. So if these people are able to switch their means, climate change, carbon capture, all is going to be much more easier. Yeah. So to do this, chemical looping, we do tests in the lab, right? So to simulate carbonaceous fuel, we have gases, we have cylinders of carbon monoxide, we have cylinders of methane, we have air, nitrogen, and all of these. And we have small scale reactors in our lab. And we have also these oxygen carriers. So we prepare oxygen carriers, different formulations of it. Iron oxide is just a very simple oxide which occurs naturally. So it could be found naturally, right? So cheap source. But there's also commercial oxides. For example, nickel oxide, copper oxide, all of these are able to donate their oxygen atoms, right? So we try to test these different formulations in different side of reactor settings at different temperatures, pressures, and so on, with also different source of gases, carbon monoxide, methane, hydrogen. And to do this, we have furnaces, we have quartz glass reactors. To analyze the end gas composition, we have something called gas chromatography. We have FTIRs. So basically all the chemistry, spectroscopy, and chromatography instruments there is.
FDIRs are those the thermal cameras?
Yeah. So FDIR is infrared spectroscopy, where you're able to analyze the end gas composition, and every gas sort of has a fingerprint, right? At different wavelength, it emits and absorbs different IR wavelengths. Yeah. So you're able to detect CO2 has a particular fingerprint at a different wavelength, and so is CO. So you're able to detect the composition.
And how is the timeline for like a single experiment?
It goes on. So because when I talk about looping, right, you talk about combustion in one cycle, and then you talk about regeneration in one cycle. One of the main criteria for a cheap oxygen carrier is its longevity, right? You need to make sure that it runs as long as it can.
Right?
Yeah, continuously. And then you need to put in a fresh batch because it's degraded beyond repair.
Right. So there's
after
like
a few cycles, there's a lifetime for every oxygen carrier. Conditions such as attrition, right? So you have particles, and maybe like after hundreds of cycles, they have just formed fines and they're not able to flow properly. Could be that they've actually lost activity, they're not able to regenerate themselves. Yeah. So things like these is why you need to put in a fresh batch maybe. And we test these for say 100 cycles, 200 cycles, 300 cycles, of different time durations as well. Some of my experiments go on for about a day. So I start my experiment and then I come back exactly 24 hours later and switch it off, and then I analyze the results. Some of them go on for 3 or 4 days sometimes. Wow. So yeah.
Okay.
Isn't carbon monoxide dangerous to keep around?
Yes, it is. It is. We we don't have the license to keep pure carbon monoxide in the lab, so we have 10% CO in nitrogen or 10% CO in argon mixture. Yeah.
So one unit that you have, when this technology is deployed, what are you selling to people? Is it you just go and plug into the exhaust of, say, a vehicle or exhaust of a thermal power plant?
So
what do people need to do?
So we're not selling this to the consumer. Okay. We're selling this to the big power plant guys, right? So example, big companies who actually produce electricity, or actually it's not even the country, it's the governments. So when it comes to governments, when they pass legislation, they have the say over what happens within their jurisdiction, what happens within their country, right? They regulate the power plants. They set up targets. They have pollution control boards. They tell the power plant industry guys, okay, look, you're going to have to pay carbon tax from now on. So for every ton of CO2 you emit, you have to pay the government so much money, right? So they could regulate them. They could tell them that, okay, look, you have to start capturing all the carbon coming out from your industry from tomorrow. And they will either do it using the 3 already established methods, or they can just innovate and try to bring in chemical looping. That's what we pitch to these guys, right? So if you get in chemical looping, it's going to make it easier. And also chemical looping offers a higher efficiency, right? Okay. So I have done simulation studies in one of my research projects. I have proven that chemical looping can offer about 42%, which is much higher than the present industry standards, which is about 37% max.
You mean after you get the gases, you use them for another turbine-like process?
Yes.
So your main goal was to capture the carbon. But as an extra benefit, you're getting a higher efficiency.
Yes.
So where is the trade-off here? What's the catch?
There is no catch.
You mean you're using the heat for other purposes? Is that what?
Yes, exactly. The heat is actually used for power generation, right? So when let's say I have 2 reactors, all right. So in one of the reactors, I have iron oxide. It's just being fluidized, so it's just being suspended in air, right? And let's say I have gas passing through, methane gas. It's going in, it's getting combusted, and the hot flue gases are going out. So these hot flue gases can be used to run a steam turbine or a gas turbine. That's one outlet, right? All of these iron oxides which are spent can be sent to another reactor which is decoupled, right? And then I can have air passing through it. And then those keep getting regenerated. So iron oxides keep shuffling between these reactors. It's called a loop, a chemical loop. And fuel just keeps getting passed, combusted, and goes another way. So power generation is taking place in one setup. Carbon capture is taking place in one setup. And then there's also regeneration happening here.
So do people need to mine more iron to do this?
Iron is just one suitable candidate.
Okay, but whatever this one is, the element that is trying to replace oxygen, then there is going to be another industry that's just dedicated to supplying this, so to say, new oxygen.
New oxygen,
Would that be a problem since people need to kind of mine it, or I don't know how do you guys make it now?
At the moment, so in research labs we just buy stuff, right? So we buy from our suppliers, chemical suppliers. But one of my parallel projects is to make sure that we have these sourced from a cheap source, right? So it's one way to do it is I collaborate with some people in Malaysia who have gone to the coastal sites and dug up some soil, and they send it to us, and then we find out how much iron content is available in that particular soil, and then I try to use it in chemical looping instead of using chemical looping from a commercial source. Buying the chemical directly, I could try to utilize the chemical already present underground. But it's one way to cheap it, so source it from cheap point, but also it's not very reliable because you can't always keep digging again and again. Right?
It's good for business because you can create another industry supplying oxygen
carriers,
element or molecules.
So there's always there's a lot of work going on in creating a lot of these formulations. Nickel oxides, copper oxides, chromium, manganese, basically any transition metal oxide could be used.
Which one achieved the higher efficiency?
The higher efficiency, so all of them have pros and cons. For example, copper gives you a lot of oxygen content, so it's generally thought of as a good oxygen carrier. But it melts very fast. So copper melts at about 1050 degrees.
Supply more. So
Yeah, and you need to keep the temperature limited. Nickel, again, a very good candidate, but nickel is very toxic. So you can't, you'll have problems disposing nickel, right? Nickel, that element itself, so it could be like a physiological hazard to people.
So nickel is used in batteries, right? It's hazardous?
Yes, nickel is hazardous, yeah. So there's issues with every sort of oxide, but the best is iron oxide because it's naturally available, it's abundant in the Earth's crust, so yeah.
Okay, so but like compared to the conventional way of generating
Power. Yeah.
from like these resources, is these new methods, are they higher in cost? Are they more expensive?
They are more expensive to the industry, yes, because if you are generating power the old way, so let's say you just have coal put in, you combust it, and then you pass it through a boiler, produce steam turbine, and that's it. You release the exhaust, right? You're not spending any money there. You're just supplying electricity to the end consumer. But once you set up a system, that's added capital cost, right? So you're trying to capture something, so you need to have some sort of machinery set up.
Right.
That's added capital cost, added maintenance cost as well. So you need to run that power plant for longer time. So all of these costs eventually add up to the industry. But so it's again a trade-off between cost versus the damage you're causing to the atmosphere, right? The ecological hazard.
Yeah, I think you go ahead.
Sorry, I guess the end result is again pushing people towards renewable energy because this extra cost again is going to be reflected on the consumer side.
Yeah.
And then people want to use less and less
fossil fuels. Yeah, exactly.
But for power producing guys, I guess the only way that they would get the technology is if there actually is a legitimate tax. Like there is a cost now for producing CO2. Then you do the math and realize, okay, there's a cost to installing this technology, but it's not as much as the cost that we have to incur, either by tax or whatever form, right? Yes. Because right now, it's an expense that it's that is not easy to justify unless somehow you're being taxed or something, some financial punishment. Right?
Yes.
Okay. I was just reading something right now because I was, someone was talking about what they did was that they captured the carbon and then used it to make methanol.
Methanol, all right.
And that's what I was asking you before we started, whether you've heard of this.
Yeah.
Are there any extremely exciting, I guess, ways that we're using the captured carbon besides putting it to the ground?
Yeah, so storing underground is just one way. You could, of course, produce methanol. So methanol economy is where methanol is thought of as a fuel. Because it's a liquid fuel, it's easier to transport. It causes less of a hazard, but also it's alcohol, so it's highly flammable to some extent as well. So you could just hydrogenate the CO2. So you have CO2. You could just pass hydrogen through it, and then you get methanol, right? You could convert CO2 to specialty chemicals, let's say formaldehyde, to carboxylic acids, a lot of other applications. Other ways of dealing with CO2. Yeah, that's pretty much it, because it's a starting reagent to lots of other hydrocarbons. So the utilization part of it is just that.
I guess you could also make diamonds. Since it's CC, right?
Yeah, it's come maybe
energy intensive it is, but I think that's what's most exciting about chemical engineering when I think about it. It's that you guys, I'm not sure if it's chemical engineers or chemistry folks, that you have the ability to create matter from like any material out of any material. You know what I mean? Like, what we're talking about here, for example, you're doing these transformations by having a proper set of steps. You can get from whatever material to whatever material. I think that's pretty exciting and very powerful.
That's the most exciting part. I'll share about my day in the lab, general day in my PhD life, right? So what I do. My supervisor has some collaborations with some people at NUS. So it's like a trifecta of collaboration. So it's NUS, NTU, and Cambridge. It's called CREATE. If you've heard of this identity called CREATE. So we're set up in NUS. The labs, they are more sophisticated in that they have a lot of funding coming from the NRF, which is the National Research Foundation. funded by the Prime Minister's office. All the funding comes directly from the PMO. Now, because of, we're thankful to the Singaporean public for their timely payment of taxes, which funds our research. Yeah, so because of that, we've got very sophisticated instruments which could go up to let's say $50,000, right? So just one, let's say just a filament or even something as much as a transducer going wrong could have a downtime of 2 months. Wow. Causing about $4,000 to $5,000 in damages and a lot of downtime, and your research just being caught up. So
this is because these things have just been released, so it's hard to find technicians.
No, it's because these instruments, because they're all very sophisticated, you also need a lot of expertise in handling them. And also their parts are very costly, very difficult to source some of these parts and so on. Yeah, so. How my day goes is I have a few projects to work on. Experimental side is one part of it, but also I simulate these on commercial softwares. I simulate these power plants. I simulate their reactions. Chemistry can be simulated nowadays. You don't need to actually run the reaction and short. You can simulate. Right. You can simulate this on softwares. So
you mean literally? I define a molecule, another molecule, and I define a reaction a program.
Yes. So you can actually set up a reactor. You can have, let's say, 100 kg of coal coming in, 100 kg of air. You can set up what temperature you want to set the reaction at, and it'll show you what the outlet product composition would be and how much of energy would that give out. So it's very cool software to do all that.
You need a supercomputer for that, or is it you solve a few equations?
It's just proprietary software, which the school has purchased licenses for. It's pretty heavy, but it does the job, and it's pretty cool. Yeah.
Okay, because I think that's really impressive, right? If you could do experiments in your room, do 1,000 experiments, that would have been impossible for anyone to do in a day.
Exactly. Yeah.
Okay, so you do experiments both in the physical world and then in the mathematical realm as well.
Yeah, exactly. It's more like validation. So you do something on the computer, and then you go back to the lab and see, okay, fine, the computer software is giving me these results. Is it possible to do it in the real world? Let's validate this. So you do experiments, and then you validate those studies.
What commercial software is this?
It's called Aspen Plus.
Aspen Plus.
Yeah.
Okay, I'll see if I can buy it also.
Yeah, it's really cool. It's actually a part of most chemical engineering undergraduate curriculum. Yeah, they usually teach these softwares during chemical engineering.
I did take some chemistry classes. They were so non-software oriented. It's just about orbitals and things like that I didn't understand. So it's nice that there's software.
Yeah.
Okay, you continue. How does your day go then?
Yeah, so I head to the lab. Usually I have some experiments lined up, so I start them early in the morning. Let's say I'm synthesizing something. So synthesizing is just you're preparing some chemical, right? So you just like add a bunch of stuff, let it heat, and then cool it down, and then do whatever pre-treatment, post-treatment you have to do to those.
Wait, but how do you plan for those experiments?
So after every meeting with my supervisor, we kind of define what the next week would go. And then he tells me, okay, so from this experiment, we've learned so much, but we need to explore a little more. So let's try to run these at these conditions and so on. So you have a plan for the next week. Okay, so Wednesday, I'm going to synthesize the chemical. Thursday, I'm going to test it. And then Friday, I'm going to characterize it. And then analyze the results on Saturday. And if things don't work, then you have to repeat again. Yeah, exactly. Yeah.
Okay, so that's like how many hours of your day?
So usually I spend about 3 to 4 hours in the lab, like actually physically present in the lab. But the rest of the time is just waiting for things to work, right? So you just set up something and you're away and just hope nothing goes wrong. There have been times when things go wrong. For example, let's say I'm trying to heat up some sample in an alumina crucible. So a crucible is like a holder, like a bowl. And then it can sustain up to 1,000 or 1,500 degrees, right? So when I'm heating, let's say, my sample in a furnace, which goes up to 1,200 degrees, there's chance that the alumina crucible might crack sometimes. So it comes back, it's all cracked, and your sample's all over the place, and you have to clean up, and you have to prepare a batch again. Yeah, sometimes glass cracks and things like that. So, yeah. So after that, there's analysis, there's writing. Yeah, it's pretty much like a standard engineering experience.
So you have to like document every experiment.
Every condition, because it so happens that sometimes something goes wrong during synthesis, and then you get these miraculous results, and then both your supervisor and yourself, both of you are stunned, and you're like, how did this happen? But again, when you create a new batch and you test it again, the replicate doesn't work sometimes. It's probably because of some contaminant or something like that. But yeah, so you got to do things at least in triplicate to confirm that, okay, things are working right. Yeah.
So this metadata, so to say, of the experiment, the conditions and so on and so forth, is there a software as well that you use for,
logging these?
Logging these, because I assume it wouldn't be...
No, it's very orthodox. It's just a pen and paper.
Okay.
So we've been given laboratory notebooks by our school. And I think at the end of our tenure, we actually have to turn those in because people who are coming after us may use them to reproduce the same results. So yeah, we just log them. So I just log how many grams of each reagent did I use, at what temperature, how many ml of, let's say, this particular solvent I add, at what temperature I run the reaction, and yeah.
That'll be hard to search though. Like, how do you know what you did at a particular... I guess maybe it works for you. I just wonder if you have 1,000 experiments, it's going to be quite hard to search. Maybe that's something someone can develop a software for these engineers.
Yeah.
Something that makes it easier.
Yeah.
Right.
Okay.
It would be nice if there's something that just automatically records what you did and how much you added.
Yeah, a lot of people try to use fancy iPads and stuff, take down notes on the iPad, but a lab is a very dirty place. It's a very hazardous place. You have, when you're working with chemicals, you always have gloves on, right? And you don't want to use stuff like that on your iPad because things can stay. One of my friends works in biology, and she told me that once she was working with cell culture and she had, let's say, bacteria on her hands, on the gloves, and then she tried to answer the phone. So she picked up the phone, so the bacteria is now on her phone screen, and then she answers the phone, and then now that bacteria is on her face. Now she has an infection for a week.
Oh, wow.
Yeah. So yeah. So it's not advisable to touch anything with your gloves on, not even door handles. Yeah.
Yeah, but I still feel that there is not much... This, because writing things in a notebook is something that the likes of, I guess, Isaac Newton were doing, right? Like, it's been a long time since then. So I feel that we could take more advantage of things like video cameras that we have now, right? Like, instead of you describing an experiment through a list of steps, imagine pointing to things. Like, I was doing this for one of my projects also, which is just documenting, like, satellite assembly, for example, right? So traditionally, you actually have a list. You move this way, take this, and so on. But if it's on video, it's like, okay, here's what I'm doing. Like, it's literally within a minute, someone understands what's supposed to be done. And I feel that maybe that could be a way to improve the communication from one batch of PhDs to the next, right?
Yeah, definitely. Yeah.
Because there are new tools, and I think we should take more advantage of these tools.
Yeah.
What is the most exciting discovery you've made, or in you specifically, or in your field in the recent years that would be worth sharing with our audience?
Right. So the most exciting was so my supervisor, I think in my first year, he approached me to work on this really exciting project, and both of us were not sure that things would work out with this. But within a span of, say, half a year, things actually did work out. Turns out it's worked out so much that we've actually now filed for IP. Okay. Yeah, we have a patent application pending. Yeah. So, and that was a side project. It was not even a part of my actual PhD thesis, but now it's incorporated, and it's kind of like the flagship project I'm working on. Yeah. So, that was very surprising, but also it's taken away quite some time from my actual focus on my PhD thesis. Because it's IP, I can't really discuss much about it, but it's along the same lines of chemical looping, but like a parallel side project. We collaborate with some people from MAE, and we've been working on this, so that was really exciting.
School of Mechanical Aerospace, no?
Mechanical Aerospace.
Yeah. So you are under the School of Chemical and Biomedical Engineering.
Yeah.
And then there was also School of Materials here at NTU. That's three. SCBE, I guess, in School of Materials there is some connection.
Yeah,
because I feel like your work sounds like material. Okay,
so
chemistry.
In SCBE, chemical engineering itself is a minority. There's a lot of people who work in the biomedical and the biomolecular side of things. There's many more faculties in that particular part of, so it's two different divisions. So we have CBE and BIE, which is the biomedical side. In CBE, we only have a few people, right? Say people working in the field of thermodynamics, heat transfer, mass transfer, and chemical engineering per se. But you have a lot of people working in biomedical imaging and just a lot of biology. Yeah, I've always hated biology. I stopped studying biology after 10th grade. I hated it so much. The last I've studied is the plant cell and the animal cell.
But just, I don't know how you cannot be interested in biology when you are a biological being. It's for your own good to know biology. Okay. And I guess one other thing that I'm personally interested in understanding from the research that you're doing is you've talked to us about the chemicals that are needed in order for you to do oxygen-less, I guess. Not oxygen-less. In order for you to replace oxygen that we use currently. And then there is a carbon capture where you're capturing the oxygen. In this pipeline currently, what is the status? What is the main hurdle as an overall technology? Where would we want to see the greatest breakthrough for people to accept this as a useful but also affordable technology for people to deploy?
Right. So I've mentioned 3 different technologies before, right? Post-combustion and pre-combustion. These would be more readily acceptable to industry because these are just retrofitting existing power plants. So you already have them burning it the old way. All they have to do is add another carbon capture facility and then have the flue gas redirected there. But chemical looping would require them to totally build a new setting, right? So because they have to bring in a chemical looping system, which are 2 different reactors, not just one where coal is being burnt. So the capital cost is higher, the operation is higher, but if you are commissioning new plants, maybe you can go for this system. But the existing power plants would probably not go for this system. So it's difficult to pitch it to them. They would probably just go to retrofit. And also the lifetime of a power plant is very less. There's about, I think, 20-25 years and then decommissioning happens. So one way to pitch this technology or for this to be implemented around the globe would be that governments start commissioning new plants with a mandatory carbon capture facility, either the old generation post-combustion or pre-combustion or something like chemical looping. Yeah, that's the way I see it. I think the pressure has to come from the higher ups, governments and industries, so that they regulate themselves.
But you mean if I wanted to build a power plant tomorrow, is your technology ready? Is my question. Can I take it tomorrow?
Yeah, on the technology readiness level, I wouldn't say that as ready because so it goes from lab scale to like a bench and then a pilot scale and then you go for like a big small pilot scale, which is like a scale down. So if you have a 10 megawatt power plant, you would build like a 2 megawatt one and then you would scale up.
The microgrid.
So we're still at that particular level. We haven't like scaled up entirely. I'd say we're still at a lab pilot where we're just testing things. This is not a very readily available technology as of today. Yeah.
And like speaking of the costs again, like does the amount of capturable carbon at the end and what we can benefit from it like financially, does it cover, could it cover the cost of this new technology?
Yes, it could. Yeah. So once you have the carbon utilized to produce some other chemical, you could sell it, right, as another industry. So that would kind of offset the cost you've spent in actually capturing the carbon. So it is quite possible. Yeah.
Okay. So where do you see this going, like in the next 10, 20 years?
I mean, honestly, there's higher chance that renewable is going to dominate the market a little more because the research and development going on from the renewable side is much more fast paced, right? So you have the cost of solar panels have been steadily going down. So it's becoming cheaper and cheaper. People are more aware, right? A lot of households are shifting They're trying to install solar panels in their houses. They're trying to switch to more renewable options. EVs are a big industry now. So the way I see it, and also that we don't have a lot of fossil fuel left. So to begin with, so for these technologies to be implemented, it's quite difficult. But the way I see it is, a few select places might go for these carbon capture systems. For example, places like Europe, where they have very strict regulations. Some countries in Europe could probably go for this. Yeah. But places like, say, India and China, US, where these are the biggest emitters of CO2, like on a per capita basis as well, it's very difficult for that entire country to, like, just up and about switch to a different system of power generation. Yeah.
But if we take just the core idea, right, like of chemical looping, could this be transferred to other industries, other
yes.
source
So
of energy?
we have chemical looping is just the concept. This science could be applied to a lot of things. We do that to produce ammonia now, right? So for example, you have some nitrides, aluminum nitrides. If you know how steel is produced, a lot of the steel waste, right, is something called as dross, DROSS. So that has a high amount of aluminum nitride. So it's waste from the steel plant. We could use that nitrogen, have water coming in, right, and that water would react with this aluminum nitride and produce ammonia, which is very different from the Haber process. The Haber process is the conventionally used process to produce ammonia, where you have nitrogen and hydrogen as two gases coming through on a catalyst and then producing ammonia. Again, so once that ammonia is produced, you have the nitrogen removed from the aluminum nitride, ALN. That could be passed. We could regenerate it by passing a separate nitrogen gas and so on and so forth. So this looping technology could be implemented elsewhere. It doesn't always need to be an oxygen carrier. It could be a nitrogen carrier. It could be any sort of thing. Yeah. This science could be implemented in different domains.
Okay, that's nice. So hopefully, if the world goes toward renewable energy, it means your technology will not have a market, but you're not worried about that because you're trying to solve the problem that renewable energy is trying to also solve.
Yeah.
But it can be applied to other areas. Because science is...
Yeah. But, I mean, again, places like India and China rely heavily on their geographic conditions, which is they use a lot of coal, right?
Yes.
So if they did, even if a few power plants went for it, it's going to be financially beneficial for them, not immediately, but let's say over a period of 5 years. Once they've covered their capital cost, once they've gotten their full set of investment back, is when they start to be beneficial. Yeah.
So Christopher was asking about the hurdles in the process.
Yeah.
But what about hurdles and challenges in your own research, like in the, let's say, like the experiments or the tools you're using? Do you find anything that's not up to what you'd hoped it would be, like in terms of carrying out your tasks?
Not really. Most of the instruments, most of the machinery we use are top of the class, right? So it's the state of the art facilities. Just recently, I visited the synchrotron facility in Singapore. It's one of the few synchrotrons we have all over the world. I think there's less than 25 or something synchrotron facilities. Yeah, it's so it's basically just like a huge donut of superconducting materials. It's just super magnets, and you have electrons flowing inside at the speed of light, right? So
I guess it'll be at almost the speed of light.
Yeah, almost the speed of light. It's about 0.9997 C or something. Yeah, it's about that much. So the Singapore one was donated by Jefferson Lab in the US, I think around 2010, and then they took over, and then they had the Singapore synchrotron light source in NUS. Yeah. So again, we've been given this, state-of-the-art facilities to use, and it's like millions of dollars of funding, so never really a problem there.
So, but I guess my question is the state-of-the-art good enough?
Yeah,
for you. Okay.
Yeah.
So then you guys should have solved the problem by now.
So we have the sources, but I think the gap is probably in literature, in that we're not able to find particular, and also it comes to problems like laws, regulations, economic costs.
Right.
Like even if you have something available, is the industry going to adopt it? Because just because it works, it's not going to be used, right?
Right,
Because
right.
there's also like a lot of costs associated with it. Yeah.
Makes sense. Well, thanks for sharing about carbon capture, about using Fe2O3
Yeah.
to do combustion.
Yeah.
That's pretty exciting. I didn't know that you could. I mean, technically, I knew you could burn things without without the traditional, not the traditional way. So this is exciting to hear that there are these very, very, very important applications. So tell us what you do besides doing research. What other things get you excited
Right.
as a human being?
Apart from research, I've been part of a lot of extracurricular activities. I've been the hall residential mentor in Hall 9 at NTU for the past 2 years. So as a part of my mentor, as a part of things that are required from me as a mentor, we organize a lot of workshops for undergraduate kids. I'm mainly involved with gardening, so I do a lot of gardening. Every other weekend, I'm trying to plant something or trying to harvest something. Yeah. Apart from gardening, we also play sports. So we play cricket, and finally we're resuming cricket now with the big field. Yeah.
Exciting times.
Exciting times. We can book the whole field and play like a proper sport. I also do quizzing. The quizzing is very it's a very underrated form, but a lot of pub trivia nights and quizzing. We have a lot of quizzing groups in Singapore, so we host like these online quizzes. It's so trivia nights really exciting for me.
Nice.
Yeah.
Didn't know there's such a thing. Like you just meet together to do a quiz.
Yeah.
Okay.
It's just a bunch of slides, and then you have like questions and answers, and people just figuring things out.
It's like a game show.
It's like yeah, exactly.
Cool.
Yeah, I also volunteer for TEDxNTU. I've been a volunteer for the past 4 years. As a part of NTU Wow, it's a flagship event, right? Apart from the hit podcast going on currently, yeah. So this year we're planning to have the event in September, 10th September. So to our listeners, please join us on the 10th of September at Nanyang Auditorium.
I hope this is out by the 10th.
I think we'll try. We'll try to get it up for the 10th of September.
Right.
Cool.
Yeah.
Exciting stuff.
Yeah.
Anything else that you think you would like to share that we might not have been able to touch on due to the nature of our questions?
Right. I think I had this idea of a podcast back in my undergrad days where, when you're looking out for admissions abroad, you have very few people to get in touch with, right? So you have social like Facebook, you get in touch with people who are currently studying there. So let's say some person from India wants to apply to NTU. They either contact the immediate seniors, people who've already studied there, who've gone to NTU, or people studying here. They just get in touch with email. But it's a very archaic form of communication, right? And all the information they get about NTU is just through the internet, right? When I was coming here, I just had like one image of NTU on Google Maps. It's just the outer building. I'm like, okay, this is how Graduate Hall 2 looks. But when I actually turn up here at 5 a.m. in the morning, I'm like, okay, this is a very different building, right? Yeah. So
true.
I think one of the ways that this information could be relayed to people all over the world is that when people start talking about their experiences, the personal experiences, for example, how much does a Ph.D. Candidate earn here? How much on average do they spend on food, right? What are the food sources available? How do they, let's say, go about shopping? How they do various things, right? Because a PhD is just not about academics, but also about spending 4 years of your life in a foreign country. Yeah. And one way to do it is to have people come in from different universities and share their experience, so that it's like a compilation of PhDs from different universities and their life in that particular university. Yeah. So so a lot of juniors from my undergrad university try to get in touch with me, and then they do ask me questions about my supervisor and research and the infrastructure, but most of the other questions are just like, how's living in Singapore, how's hall life, how would it be if I lived outside, is it going to be monetarily possible for me, am I going to save up stuff, how's the food, is there a lot of Indian options available, like those questions which you have to tackle on a day-to-day
Yeah,
basis. Yeah.
That's interesting.
Yeah.
I think in the future, hopefully, we can actually have folks from other universities here.
Yeah.
And then I think we're going to branch out to make it into a more accepting people from even non-Singaporean universities. Because we think that there is something common about PhD here as well as at, I don't know, Cambridge. Like you're connecting with them. And I think that at the end of the day, this podcast was built with that in mind, right? To share the tools. That's why we ask you specifically, what are some tools you're using?
Yeah.
Because ultimately, not so many people know what we do as PhDs, but also they don't know what tools. Some people think it's very hard. Some people think it's not, whatever. But I think the point is that the more we talk about how you do a PhD, the more people can understand whether they are suitable to do it. And so that's a very good point. Okay.
And on that note, Syed, thank you very much for joining us. We
you
really enjoyed talking to you.
I love it though.
All right, thanks, and bye-bye for now.